Now, coming back to the charge generated, and if you want to use it as a sensor,
Right.
let's say some vibration sensor or something,
Okay.
then, I mean, of course, this is the model that we have discussed. It is generating some, let's say, some charge QP. It has got this capacitance CP and then the resistor.
Correct.
What I would like to get is a voltage corresponding to this charge.
Yes.
So, ideally, all the charge generated this, I would like to get here.
Yes.
I mean, a corresponding output voltage.
Yes.
So, for that, I need to transfer all this charge to this capacitor.
Correct.
Correct?
Yes.
So, if QP is generated, let's say the whole charge reaches CF, then that QP by CF will be the output voltage.
Correct.
CF is known.
Yes.
So, let's forget other components for now.
Okay.
Let's say you have, for us, let's say this is shorted and this is open circuited. Let's say if you, this capacitance can be there. Let's say it's like this. You also leave this half VCC now. Right?
Okay.
Let's say it's ground to start with. Then this is also at ground, this terminal. This is, or these two are at same potential, correct? Because of the negative feedback of this op amp. So, if these two are at same potential, then whatever charge generated here has to flow through this way, because this capacitor cannot charge now.
Yes.
So, that means it cannot enter this, so it has to flow through this.
Because
So,
they are at the same potential.
yeah.
So then he has to go to the capacitor.
Yes. So, CF will get QP charge,
The full QP charge.
full QP charge. That QP by CF will be the output voltage,
Yes.
right?
Yes.
Now, if your op amp is only operated using plus VCC, there is no minus VCC, because the QP can be positive or negative, right? Here is positive, so it went to minus volt, negative voltage, plus minus QP by CF. So, if you are powering only with positive voltage,
Only one range.
yes,
Yes.
then it cannot go to negative side.
Yes.
So, what you do is you shift this voltage by half VCC. So, this is also at half VCC. So, you will have a VCC by 2 already at the output. When,
okay.
yeah, when no charge is there, you have a half VCC.
So that's like an offset.
Yeah, it's an offset.
Yeah.
So, from there the output change up or down.
Okay.
Right. Now, you see some other elements here, CC, one thing, which is you have this piezoelectric element, then you have used a cable to connect to your circuit. Cable will have cable capacitance, we have discussed this before, which should not actually affect, we do not want it to get affected or the charge transfer to get affected. So, again let us assume this is very low, because these two are at same voltage, CC cannot charge.
Yes.
So, it does not affect the charge transfer. So, the internal cable capacitance will not affect our charge transfer. So, that is good. Now, why this RF? Because when you use op amp will have some bias current, IB minus in this case,
Okay.
right? Maybe going in or coming out depending on the first input stage. Now, this current has to come from the output. If you have only this capacitor, it will be coming through that.
Yes.
And it will, once you turn on the op amp, it will be keep always flowing.
Right.
So, it will charge the capacitor and go to saturation in, in milliseconds,
Right.
depending on the capacitance value and bias current. So, you cannot actually use it. Now, what you do is you give a RF in parallel to that.
Okay.
So, whatever the DC IB side DC current, so charging that is happening, you provide a discharge path.
So rather than going back into the up, we will go through the RF.
Yeah. So, now if CF gets charged to a DC voltage, it will also discharge through RF.
Right.
So,
And how do you choose this RF value based on the
yeah, so
impedance of the
so that, see, for the piezoelectric sensor, you know some range of interest that you will have.
Yes.
So, once you have this RF and CF here, the impedance of this, it will become it's a parallel combination of this. So, RF into 1 by, yeah, CF. So, j omega CF will get cut in the numerator. So, this will become something like this.
Yes.
So, let us say for frequencies where omega RF CF is very low compared to 1, is just RF, right. For the other case where omega RF CF is very large compared to 1,
then RF
it's almost R of RF will get cancelled.
Yes.
It will be 1 by omega CF.
Yes.
So, that is the region where we want to, you know, see, it's almost like RF is not present there, right. So, for low frequencies, okay, RF will serve as a discharge path, while for higher frequencies higher than, I mean, we can calculate from this, it will serve as a, mostly it's what is present is this capacitance. So, that is how you get this, this point 1 by R of CF, 1 by 2 pi R of CF. So, frequencies higher than that we are interested.
Yes, because it's constant gain.
Yes. All the charge that is generated here is converted into a voltage here. So, you actually call it as a charge amplifier. I mean, you can choose the value of CF that you want to adjust the gain. And as you see here, it's independent of the value of the frequency, because here you don't see omega in the,
no.
Yeah. Now, maybe students can figure out why this is happening, right. See, I have not talked about RI so far, right. So, see, we have also talked about impulse. I mean, in the case of a gas lighter, you are giving an impulse. I mean, you are slowly pressing, but once it reaches a threshold, a mass is moved and hitting on the piezoelectric stack.
Yes.
Right. In fact, stack. So, inside there are many layers of piezoelectric material. You are going to give a hit. All these voltages add together, becomes a very large voltage.
Creates a spark.
And then there is a small breakdown of that air between that center point and outside ring happens, and that is how the spark is formed.
Right.
Okay, why did we go there? Anyway,
no, you're talking about that equation, right? How to get that equation?
Yeah.
Yes.
So, when such things happen, it can actually, such inrush current can actually damage this
op
amp. So, this Ri is a small value, but it suppresses such inrush currents.
Kind of absorbs that.
Yeah. So, it can no more be impulse. It will be a smoothened impulse. Right. So, students can look at, if you have this Ri present, what characteristic it will give. So, we will see that it will introduce another pole here, and from there output will reduce. Right. So, it is a nice example of a charge amplifier. They can actually read more from this Texas Instruments application report. There is also, this is a charge amplifier where cable capacitance will not matter in this case. But if you are only interested in voltage, you can also use a voltage amplifier. There is another design given there, where the cable capacitance has to be very small, otherwise it will affect the
Right.
final output.
Right.
Yeah. So, brief about piezoelectric, how to use it as a sensor, and you can also use it as an actuator if you are giving an electrical signal. Right? As you pointed out, output, you can get an output for dynamic input, not for
single.
I mean, yeah, if you keep a DC input as a mechanical DC input, you get one spike and then there will be more, right? So this needs to be registered. Otherwise, when you design sensor, so you were also mentioning about harvester.
Yeah.
So what is that? Harvester means, I know,
because somehow you're getting a voltage.
See,
right?
for me, harvesting means harvesting
The
vegetable farm.
No, because you said, I mean, initially you were talking about you apply a force, you get some voltage, right?
Mm-hmm.
So that means if you can have something that produces that force over a long period of time, maybe somehow your output will also then change according to that voltage or that input.
Mm-hmm.
So then if you have, let's say, I don't know, some capacitor, you can probably store that charge and use it for something else.
Okay,
Right?
Okay. So, I mean, this is a nice example of a fan, but let's say this strip is available and then it's exposed to some kind of vibration.
Yeah.
Then there will be voltage generated, or there is some energy conversion happening there.
Yeah, mechanical
to electrical.
Yes.
So this could be used.
Yes.
That's
Maybe
what
it can
you're
be
saying.
stored somewhere and then used.
Use it. Okay. So it could be used for powering small sensors and so on.
Exactly.
Of course, it will not generate
huge amounts
watts.
of voltage.
It will generate some microwatts.
But we don't need watts, right?
Yeah. So, I got it. So from the ambient vibrations and so on, if you can convert into an electrical energy, you are actually harvesting energy.
Yes.
Or scavenging energy.
Scavenging.
So this is the energy harvesting.
Right.
Oh, nice.
And I'm sure there are lots of different vibrations, right, in real life.
Yeah.
Maybe you can exploit.
Yeah. So maybe students could read more about
That's true.
energy harvesters.
Yes.
Because this is very useful for powering sensors where you don't have this kind of 230 volt power supply available.
That's right.
Or even if you use battery may not be available forever.
Yes.
I mean, it works for some time, then you will have to replace.
Exactly.
So if it's not easily accessible location, then you cannot go and change battery all the time.
That's true.
So it's good to look at what are the ways in which you can scavenge energy from the ambient. It could be even sunlight.
Exactly.
So piezo is one of the ways where you can get a vibration to energy conversion. Nice.
Very nice.